Okay, this is a video in case you missed our discussion after the Newton's First Law lab. And so let's go way back in time to the days of the Greeks and the philosophers. They weren't really scientists. They would write their ideas and argue their ideas, but rarely did they actually test them in a controlled way, as we know science is done. If you wrote about the natural world, you were a natural philosopher. So these were the precursors to scientists anyway. And the Greeks had some ideas that maybe don't make a lot of sense now, but I think if you put yourself back in their time and based on what they knew, the sort of ideas they came up with can make a lot of sense. They thought there were four elements, a lot easier to memorize the periodic table back then. And so you had your earth, air, fire, and water. And all the things you saw around you were made up of these elements or combinations of their elements. And according to Aristotle, there were two types of motion. Natural motion, which did not require a force to carry out, and violent motion, which did require a force. Natural motion is one of the elements trying to make it to its natural place. So here you see some air bubbles, which are clearly underwater. That's not where they belong. They belong up in the air, so they will just rise up into the air, and no force is required for that. Now keep in mind, I'm explaining what the Greeks thought, not what we currently think. I wouldn't take notes on this. Here we have somebody burning something, and the parts of the thing you're burning that are consisting of air and fire are rising up to take their place in their natural realm. And then what would be left over, the ashes, well, that was the earth part of whatever is burning here. And so no force was required for this. Violent motion is when you displace something from its natural place. So you push the bike uphill. If you stop pushing, the bike will stop moving. Now we know now that is because there are other forces still acting on the bike that slow it down and stop it. In this case, might even have it roll back down the hill. And so again, from the Greeks' perspective, here is an arrow which has a lot of earth in it. And so to displace it from the earth up into the air requires a force, the force from this bow. And once the force from the bow is gone, the arrow keeps going. And so that's where they had trouble explaining that. No force was on it, and yet in the direction it's moving anyway, and yet the arrow kept going. And so they would come up with ideas that the arrow was leaving a vacuum behind it, and the air rushing in to fill the vacuum propelled the arrow. That doesn't really work. It actually makes it so the arrow is going to slow down even more. And so the ideas of the Greeks at least gave you an initial way to think about things, but they weren't tested, and that was the case for hundreds of years. People would just memorize what the Greeks wrote, and then they would be learned individuals. It wasn't until others started to propose that your senses should also be involved in what is knowledge, and then that you can create experiments to test other people's ideas and your own. And Galileo was one of the first proponents of that did it in a systematic way. And here I'm going to go through some of his arguments. He would make that Aristotle was incorrect about a force being required for motion, at least the violent motion that we were talking about. And so Galileo would roll objects down a ramp, and of course he would notice them speeding up. Now Galileo also noticed that they sped up at a constant rate, and was able to write equations that would tell you where the ball is going to be as a function of time and how fast it's going, the equations of kinematics that we use today. And he wasn't just going down to the Home Depot and buying a board and getting a bocce ball. He would make instruments that were very elegant and precise. He had this huge workshop, and we'll see some of his instruments in a little bit. And then if you roll the ball up a ramp, it would slow down, again, at a constant rate. And Galileo would argue that there's got to be a transition ramp where the ball would not be speeding up or slowing down. It's transitioning in between the two. And so this would be the transition ramp where the ball would just keep going and going forever at a constant velocity, without any net force on it. Now, we know if you did this in experiments, the ball would roll to a stop on a level ramp. But actually, if you tilted the ramp slightly downhill, you could do it so that the forces slowing the ball down, the rolling resistance and air resistance, would be canceled out by the downward force of gravity, the component of gravity in this direction. So it is possible to construct a ramp that would have a constant velocity ball if it was tilted slightly downhill. So Galileo would make this argument that Aristotle was incorrect in saying a force was required for motion. And he didn't just write it in Latin and share it with scholars. He wrote in Italian. He published his ideas in popular books that were bestsellers. And he would go out and argue with people and get them arguing, to get them to challenge ideas that had held sway for hundreds of years. Here's another argument he had, that objects, once in motion, would continue in motion, is he would roll a ball down a ramp and find out that it would almost reach the same height on the other side. Maybe he would notice a little bump in his ramp and he would fix that, or maybe the ball was imperfect and he'd make it more round and it'd get a little closer to the same height. So you could see ideally the ball was reaching the height it started from. Now, we just sort of take that for granted, but if you really think about it, that's pretty mysterious. How does a ball know what height you released it from? It turns out that is the idea of conservation of energy, which wasn't fully developed until the 1800s. So Galileo was way ahead of his time with these thoughts. Well, it didn't matter how he constructed the ramp, the ball would still try and reach the same height. So if he had a different angle on the up incline here, it would still try and reach the same height. So he said, hey, let's fool the ball and never have the ramp go back up. So would the ball just keep going forever trying to reach its original height? Again, if you do it in practice, you could tilt the ramp slightly, as I mentioned up here, but in general, you see balls slow down and stop. And Galileo would say that's because of the other forces on it, not because you've removed any forward force. And so you got people talking about new ideas, and other people started doing experiments, and this was really the birth of science. Now, Galileo was interested in motion, but he also had an alternative motive. He was also trying to develop support for the Copernican model of the solar system. And here's some of his actual instruments. And so here's a ramp, very smooth looking, very beautiful instruments. And another ramp connected to it so he could compare the speed of the ball going down the straight ramp versus the curved ramp. This one, these bells are movable. And so he would put the bell, and as a ball rolled through it, it'd make a little ding. He would move the bells until he heard the dings at regular intervals. And he would find out that the total distance the ball had gone to that bell varied by the time squared. And so you're pretty much seeing the 1/2 AT squared equation by the spacing of these bells. And so back to Copernicus. So Copernicus was a Polish monk and astronomer that published a book with his idea that the planets and the Earth were all going around the sun, not the sun and the planets going around the Earth, as the Greeks, especially Ptolemy, had proposed. And one of the arguments against the Copernican theory, there actually were a lot of arguments, scientific arguments against it. The lack of observed parallax was one important one. Galileo just said, well, the stars are really far away, but they really didn't explain it that well because they couldn't show how far the stars were. But one of the arguments against the Copernican theory was citing Aristotle, that if the Earth is going around the sun, then the cause of the day-night cycle is the rotation of the Earth. And they knew how big the Earth was. They could calculate that it was, for somebody on the equator, this rotation caused them to go 1,000 miles an hour. Well, they thought it was absurd that you could be going 1,000 miles an hour and not notice some effect from that. Shouldn't there be a great wind blowing? Wouldn't you feel it? And then they also thought that to make something go 1,000 miles an hour required a force. And that force would have to be due to your contact with the ground. So if you were to jump in the air, all of a sudden you would stop, but the Earth would keep rotating. And so you would go flying off toward the west, apparently, and run into things and be killed. And so nobody would jump if that was the case. And so if you jump up in the air, that doesn't happen. You just go straight up and down. And so they said, see, the Earth can't be rotating. Galileo said, yes, it can. When you jump up in the air, the Earth keeps going in this direction. You keep going with it. And so it looks like you land back in the same spot. But really, you and the Earth moved quite a bit during that time. Just as if you're on a bus going to constant velocity and you jump up, you will land back in the same spot on the bus. And so he developed these ideas of motion to also support the Copernican model. And it turned out he was correct. Now, Newton adopted Galileo's ideas about objects in motion would tend to stay in motion and at rest tend to stay at rest. One tiny difference, Galileo thought the natural motion of objects once you got them moving was following the curvature of the Earth, where Newton realized it was a straight line. And so it's a sort of minor difference because any experiment you're going to do is not going to really show much curvature to the Earth, but there was a small difference. And so Newton's idea is captured in this statement. Uniform motion I'm going to use in this talk to mean constant velocity. And so when you see that term, think constant velocity. And our textbook said if no force acts on a body, we can always find a reference frame in which that body has no acceleration. Really, I'd rather see it say if the net force on a body is 0, we can find this, but this is a true statement. And it shows you that if you're in a reference frame that's accelerating, you won't think Newton's first law is applying. So you need to be in an inertial frame of reference, one that is not accelerating. Then, of course, there's Calvin's version of Newton's first law. Explain Newton's first law of motion in your own words. And he doesn't know. And then he goes, oh, wait a minute. I can just make up my own words. And so that's his loophole. Try that out in your English class sometime. See how it goes. Probably about as well as it did for Calvin. Often we use Newton's first law as a time to talk about the difference between mass and weight. And so they are two different things, very different. There's a relationship between them, but keeping in mind that they're different and knowing which thing it is you need to be figuring out in a particular application is going to be a struggle pretty much the whole class. And so inertia is a resistance of an object to changes in its current state of motion. In other words, resistance to acceleration. And so you can measure the inertia of an object by seeing how much force is required to cause a given change in its motion, a given acceleration. And this measurement, we call its mass. And so our mass and inertia are the same thing. Pretty much, mass is a measure of how much inertia an object has. And in physics, we measure it in kilograms. So we use the MKS system, meters, kilograms, seconds. So instead of using grams, we use kilograms. It makes some of the equations easier. That's why we do that. Now, weight is not a measure of resistance to acceleration. It's how hard gravity pulls on an object, and we measure it in newtons, not in kilograms. And a newton is like a pound, but it's a metric version of a pound. Mass doesn't depend on your location. You're always going to have a resistance to acceleration, whether you're on the moon or Mars, in orbit about the Earth or on the Earth, that resistance is going to be measured to be the same. And that's actually how they measure the mass of astronauts on the International Space Station. They apply a force to them and they measure their acceleration. They have a little gizmo that does that. Weight does depend on where you're at. And so weight would be a certain value on Earth. Let's say you had a weight of 1,200 newtons. On the moon, that weight would be 1/6, or only 200 newtons approximately. And so you would definitely feel a lot less weight, but your mass would be the same. The Apollo astronauts found that out. With their backpack and their spacesuit and everything, they were about 360 pounds on Earth, only 60 pounds on the moon. And so they could jump and hop and walk, and it seemed really light. But when they tried to stop, the mass was still there. The same amount of force was required to make them stop, and they often fell over as they didn't anticipate that until they eventually grew used to it. They'd slow down gradually. Now we can calculate weight if we know the mass and the gravitational field strength. And so this is the relationship. Gravitational field strength has a direction. It's down. I multiply by the scalar mass, and I get the weight vector. And its value would be the mass times little g, and little g on Earth is 9.8 newtons per kilogram. So from now on, you need to be able to calculate the weight of an object given its location here on Earth, in this case, and its mass. And then you should be able to do the reverse. If I told you its weight and the gravitational field strength, you should be able to calculate the mass. The hard thing won't be this calculation. It'll be knowing, do I need the mass in this case, or do I need the weight? And so if you need a force, you need the weight. If you need the inertia, then you need the mass. Now, you may get used to this idea and do pretty well in this class, but I suspect some students afterwards kind of say, well, back in chemistry, we didn't distinguish mass and weight. I got an A. I'm just going to go back to that after physics. Life's complicated enough. Why make it more complicated? Well, let me show you why that's going to ruin your life. So you might not realize it, but in the future, you are going to own an import-export business. You're going to buy products in one place and sell them in another place and make a tidy profit. Well, you've just negotiated the biggest deal of your career. If you pull this off, you could retire. You have negotiated a really good price on a tanker load of Finlandia vodka. And it's such a good deal that you're going to sell it, be able to ship it and sell it to the place where it's the most popular drink down here in Ecuador. And so Finlandia is purchased up here in Finland. Actually, they make it at the northern regions of Finland, almost at the North Pole. And of course, Ecuador here, down named for its location on the equator. So when they're negotiating the deal, they ask, do you want to buy this as weight or mass? They're like, it doesn't really matter. Maybe in physics it did, but I know it doesn't matter. I'm going to buy it in terms of weight. And so they load you up with 100,000 tons. And so ton is a unit of weight, 2,000 pounds per ton. You can figure out how many newtons it is. And then you are on your way to Ecuador. So you pass down through the Atlantic, dodge that tropical storm, through the Panama Canal. Now you unload your cargo in Ecuador, and they weigh it and pay you. And when you get your check, turns out you were missing 600 tons of vodka. And it wasn't the crew. Captain Hazelwood wasn't in charge. You are missing 600 tons. It's not there. It wasn't consumed. What happened to it? And so if you think you want to figure this out, pause the video, see if you can figure it out. I'm just going to continue to explain here. Usually somebody knows this. The Earth is not perfectly spherical. And so when it was formed, it was molten, and it's rotating. It's still partially molten in the interior. And so it actually bulges out a little bit at the equator. You're about 12 miles further from the center of the Earth at the equator than at the pole. And because you're a little bit further from the center of the Earth, if you use Newton's law of gravity, you can calculate how strong gravity is. It's a little bit weaker because you're further from the center than at the pole. And it turns out that little bit weaker when you have 100,000 tons is a lot of vodka. And so that was your whole profit margin and then some. Your company's now bankrupt. You're destitute, all because you didn't listen to your physics teacher. But don't worry, we'll give you a chance to redeem yourself later. So here's some questions. I'm going to let you read the question after you pause it, and then I will go over the answer. If you just watch this and read the answers as I go, you're going to get very little out of this. You might as well just stop watching. But if you participate, pause the video now and read this, and then I'll give you the answer. And then as I go through the other ones, I will remind you to pause the video. And so the answer here is none of the above. The jet is at rest on the runway. Well, it could be that. Let's go of a cell phone. It would fall straight down, hit a spot directly below it. But that's also going to happen if the jet is cruising at a constant velocity. And so I can't conclude which one this is so it's none of the above. If the jet was speeding up or slowing down, then as the phone fell, the speed of the plane would change a little bit relative to it in the horizontal direction. It would land at a different spot. So the plane would continue accelerating horizontally. The phone would no longer accelerate in the horizontal direction, and so it would land in a different spot. Okay, again, another question, so pause it. Here comes the answer. And so impossible to tell. So again, uniform motion, constant velocity. And so you might say, oh, wait a minute, a radar detector would say that. Well, if I point a radar detector at a car that's moving toward me, it'll measure its speed. But if the car is parked and I run at it at the same speed, it would still measure that. I can't tell if it's me moving at constant velocity or something else. And we already saw dropping the ball, it's going to land in the same place. So that's not going to tell you. Uniform motion, that's constant velocity, you won't feel that. What you feel in a vehicle that's moving with what you think is constant velocity are tiny deviations from that. And so a jet that's at altitude with no turbulence, that's cruising, that is probably as close as you're going to get to absolute constant velocity, and you don't feel anything about it. Maybe some vibration from the engines, but in a large plane, that's pretty hard to detect. Trains can move fairly uniform, and so oftentimes you'll be in a train waiting to go, and then all of a sudden you'll think your train is moving, and it turns out, no, you're still stopped. It was a train next to you. And if you don't see anything moving, you're at rest. Well, everything could be moving the same way you are. And actually, if you think about it, that's what's going on right now. I'm assuming you're on Earth. So if you look out the window, everything you see, the trees and houses and everything is rotating around the Earth along with you. And so you conclude you're at rest. And so we know that's not the case. So it is impossible to tell. You can usually use your reason to figure out if you're the one moving relative to something else or not, but it's really impossible to do a physics experiment to tell. If there's acceleration, then you're going to be able to detect that with an experiment. And here's another question. So again, pause it and read this and think about it and answer it, and then I'm going to go over it. And so it's A or C. And so let's say at first you threw the Frisbee, the dogs ran to get it, and this one pulls with 100 newtons, and this one pulls equal and opposite, 100 newtons, and it's a doggy tug-of-war standoff. And so the Frisbee is at rest, it's just sitting there. But then this dog decides, I really want that Frisbee more than the other dog, so he starts to pull with 110. So now this is going to start to accelerate to the right, and it's going to increase to some speed. And at some point, this dog says, no, wait a minute, I really want it. He pulls with 110 newtons. So now I have two equal and opposite forces acting on the Frisbee that's already moving, and so it's not going to accelerate. It's going to remain in uniform motion, constant velocity, moving to the right at whatever speed. And so sometimes it helps if you don't have to wonder how it got moving, but once it's moving, if I balance the forces, it'll keep moving at constant velocity. So maybe this one's a little more something you have experience with. So again, pause it, read this, answer it. And here's the answer. And so it doesn't really matter whether you know how a car works or not. If you understand Newton's first law, you know that the forces acting on the object have to add up to 0. And so the forces pushing the car forward are the same value as the forces pushing backward. They add up to 0. And so you can have constant velocity. And 0 velocity is constant velocity as well. That'll be one of the things you'll have to remember. And so the force pushing forward on the car is the road. So the wheels are spinning this way, the road pushes forward on the car. And the force that's pushing backwards, well, at 65, that's mainly going to be air resistance. And so there's a lot of air hitting that car. If you try standing up in the back of a pickup that's going 65, you'll see what I mean. try holding up a big sheet of plywood and you'd go flying out. And so there's a large force from air resistance on the car, and when those two are balanced, the car goes constant velocity. If you want to speed up, you push on the accelerator. Well, that causes the tires to push harder on the road, and the road pushes harder forward on the car. You start speeding up, but then the air resistance increases, and you end up balancing it again at some higher speed. If you want to slow down, you take your foot off the accelerator, and the car then will have a larger air resistance force pushing back on it, and so it'll start to slow down, and it'll keep slowing down until it stops unless you put your foot back on the accelerator. And if you thought E was correct, well then it's not correct. So I promised you I'd give you a chance to redeem yourself with your big import-export failure. So I have an opportunity for you to invest in this business that I'm starting. There are a lot of really important, rich, powerful people that live in Washington, D.C. and travel to California all the time. And that's like a 5-hour flight. They've got important things to do. If they want to just go home for the weekend, that's 10 hours sitting in a plane. So what I've done is leased a fleet of luxury helicopters. And so we'll get these clients to board our helicopter, and they get in, and then the helicopter is just going to take off straight into the air and hover. And then the Earth is going to rotate underneath, and then when you see the Golden Gate Bridge, they land 3 hours later. And so we've shaved almost half the travel time off, but with this idea. Plus, they're in this nice, comfortable helicopter, and all they have to do is hover. So if you want to invest in my idea, please send me your checks. But if you're skeptical, you should be, because we already sort of talked about this. When you jump up off the ground, you don't land in a different place because the Earth is rotating. You keep moving with the Earth and land back in the same place you jump from. That's all the helicopter is doing. So it goes into the air, but it's already going at this latitude about 800 miles an hour due to the Earth's rotation. It keeps going 800 miles an hour, so do the buildings and all the people in Washington, D.C. So 3 hours later when they land, they're still here in Washington, D.C. And you might think about going into space for this. Well, helicopters don't work in space. You could use rockets, and there is a slight little difference in speed as you move away from the Earth, but that isn't really what's going to do it. It's the speed of the rocket. So if you were hesitant to invest in this business, you were catching on to Newton's first law.